Okay, recap of last time. Essentially, current can't disappear. It has to go somewhere, right? So just as a review, what is the value of I in the below diagram? Yeah, go for it.
Uh, 4 amps.
Yeah, do you want to explain why?
Because the current that is going in is 5 amps, and the current that's going out is 9 amps currently, and 9 minus 5 is 4 amps.
Yeah, because we have to have an equal amount of current going in and going out, right? And that's essentially what we talked about last time. Okay. Similarly, voltage adds up to zero around a loop because we can't just have like a big difference of voltage. That doesn't make sense. And if they didn't add up, weird things would happen. And this is true for any loop in any circuit. So this is like a universal rule for circuits. Current can't just disappear and voltages add up to zero around a loop. And then another thing we talked about is that resistors follow Ohm's law. So remember V equals IR, or if we rearrange it, we can also say I equals V over R, which is electric current equals voltage over resistance. And then we also went over power, right? Power equals voltage times current. And everything follows the power relationship. So quick question, 5 amps of current flow through a 10 ohm resistor. How much voltage does it drop? Satvika?
It drops 50 volts
Yeah. Why is that?
because the voltage drop formula is current times resistance, and then the current is 5 amps times the resistance, which is 10 ohms. So 5 times 10 is equal to 50.
That's correct.
Right.
And then how much power would this dissipate? Naman, if I'm saying that correct? Or,
Yes. 250 watts
and why is that?
because it's 50 volts times 5 amperes, which causes 250 watts.
That's right. Okay. If 5 amps of current flow through a 10-volt battery, how much power does that dissipate? Idea, if I'm saying that correctly?
Um, uh, 50 watts
And how'd you get there?
because the power formula is P is equal to VI, and the I is current, and the current is 5 amperes, and the voltage is 10 volts, and 5 times 10 is 50.
Yeah, so you all fell for my trap there. It's negative 50 watts. And this is really important because I use the word dissipate, okay? A lot of the time when we do analyses with voltage and power and circuits, we can get messed up on the signs. And so we like to think only in terms of dissipation. Resistors dissipate positive power and batteries dissipate negative power. Getting rid of negative power means you're adding in positive power, right? So in future problems, you might see that we're saying the battery supplies or the battery is dissipating negative power. Don't get tripped up by that. That's just saying it's supplying positive power. That's why I asked that question. Okay. And also, just keep in mind also, just if you ever do circuits in the lab, multiple amperes of current is very unrealistic. Actually, like today, I was in the lab and we had one of our fancy devices have 3 amps of current run through it and it basically exploded. Okay. And it's like a $20,000 thing. It's actually a big deal. But the point is, in the real world, you deal in milliamps, 1,000th of an amp. Okay, so an amp is a very large amount of current. Anyways, keep going.
Yeah. So we've already like learned these laws, right? We've already talked about it. But remember our assumptions, we should state them more formally. So instead of having these like incorrect things, we can talk about them as in Kirchhoff's current law and Kirchhoff's voltage law. So Kirchhoff's current law, or the junction rule, is essentially just what comes in must go out, right? We need to have an equal amount of current going in and going out for the circuit to work. And then Kirchhoff's voltage law, or a loop rule, if I go in a circle and come back to the same point, my voltage has to be the same. because it doesn't make sense if it's different. That would mean there's like infinite voltage. And then this is true for any loop in a circuit, but you have to be careful with signs because it gets kind of confusing depending on which way it's going. And we'll go over some examples so that's more clear. And then I'll hand it over to Ishan.
So, okay. So suppose I give you a circuit like this, okay? And I tell you, hey guys, let's find the power that battery supply. Because remember, power is what counts. And if I want to tell you, if you want, someone might ask me, how much power do I need this battery to be rated for? I can't just tell them like that. Can any of you in the next 5 seconds tell me how much power this battery supplies? The answer is no. It would take you at least a minute or two. Even if you know the tricks, it would take you about a minute. Okay. So the way we deal with those, sometimes if the circuit is simple enough, the first trick up our sleeve for circuit analysis is simplifying series and parallel resistors. A lot of you have probably seen the formulas for that. If you haven't, that's great. But rather than just presenting those formulas to you, we're going to derive them real quickly. So first of all, suppose we have this series circuit right here, a 5-volt battery in series with resistor R1, R2, and R3. We're just going to use variables for that resistance. So variable for R1 is R1, the variable for resistor R2 is R2, and same for R3. Okay? Write out Ohm's law for all of them. So the voltage drop by that first resistor is IR1, the voltage drop by the second resistor is IR2, and the voltage drop by the third resistor is IR3. Again, notice the current through all of them is the same, okay? Now let's add those together. IR1 plus IR2 plus IR3 equals I times R1 plus R2 plus R3. Now, that looks a lot like Ohm's law, V equals IR, but with R being equal to R1 plus R2 plus R3. Do you see what I mean? And so instead of using these three resistors of R1, R2, and R3, we can just rewrite those three resistors as a single resistor with the value of R1 plus R2 plus R3. Does that make sense to everyone why we would do that? Someone tell me why we would do that. Just, it's kind of a weird question, but what's the advantage of doing that? Yeah, Naaman. Naman. Sorry.
Is it kind of like the distributive property?
Math-wise, yes, that is the distributive property that we use to simplify that. But in terms of circuits,
because in series circuit, you're just adding up more resistance. Like the path is like you only have one path, so as there are more resistors, so as there are more resistors, there more resistance. It adds up like that.
Yeah, you're saying the right thing. My question was a little poorly worded, but it's what Neil said in chat. It is just simpler. It's easier to analyze this circuit because then I just do 5 volts divided by R1 plus R2 plus R3 and I get the current. In this circuit, even though like it seems if you know to add them together, yes, then you're fine. But just like that, without knowing that you can add them together, it's obvious that you should do that. And this is particularly important when we look at parallel resistor networks. Now it'll become even more clear because now if I tell you to find the current, you don't just add them together. You can't, right? And if you know the formula for this, which we're going to show in a second, you know the formula is a little wacky too. So here, the current that goes through all three of these is not the same, right? The current that goes into this point right here splits into current that goes down through all of here, and then it recombines into this bottom current, which is cut off, but it says I. But the voltages dropped are all the same. I just flashed it for a second, but can someone tell me what the voltages dropped by those resistors are? Yeah, 5 volts, true. Yeah. And then what is the current that goes through each resistor? Yeah, Naman?
Is it IR1?
That's true. But if I were to write it in terms of voltage and the resistance of each of them. Yeah, Avatar Nandan?
The current would be like have to add up to the amps that is going into the like each junction.
Yeah. Or it's like Toby, who is an instructor and should not be answering questions in place of the students that are trying to learn, said it's V over R1, V over R2, and V over R3. Okay? So that's what I show right here. And because that's just Ohm's law, right? The voltage drop by each resistor divided by the resistance of the resistor is the current that goes down. So V over R1, V over R2, V over R3. Does that make sense to everyone? Is that confusing to anyone? Okay, so we're good on that. So now we know that the sum of those three currents has to be equal to I, right? Because I goes in, and then there's nowhere else for that current to go. It has to go down there, or down there. There's nowhere else that it could go. So I equals V over R1 plus V over R2 plus V over R3. Let's factor out that V. And now here's the weird step that is going to look a little confusing. If you remember, I equals V over R, right? Ohm's law is V equals IR, so divide by R, I equals V over R. So let's write this in the form of I equals V over R. We take this 1 over R1 plus 1 over R2 plus 1 over R3 and take the reciprocal of that and move it to the denominator. Okay? It's a math trick, and I can, if that's confusing, I can write it out for someone if they would like me to. But we are able to do that. And so yeah, that's okay. So what is 1 over 1/5? 1 divided by 1/5.
5.
Just 5. It's just 5, right? We're doing the same thing here. 1 over a number is equal to the reciprocal of that number, right? Or 1 times a number is equal to 1 over the reciprocal of that number. If the math is a little confusing, it's okay. The point of this is that we can rewrite the resistance that we just showed in a simpler form. So let's look at the left first. Look at the left of the screen. We can combine these three resistors, R1 plus R2 plus R3 and so on, into a single resistor with the resistance or equivalent resistance of R1 plus R2 plus R3 and so on, okay? We can do a similar thing with the resistors on the right, but the formula is a little more complicated, okay? It's 1 divided by 1 over R1 plus 1 over R2 plus so on, okay? So if that derivation was a little confusing, it's okay. We're still new to these things, but you should recognize these formulas at least. Does the formula make sense?
Yeah.
Okay. Yeah, if anyone is still confused, is it like arithmetic sequences? Insofar as you add things together, yeah, I guess it is. That's true. Okay, someone said they didn't get it. Let me explain one more time. So if we're looking at this series of resistors, right, the sequence of resistors right here, this is quite nasty, okay? And so this is not at all easy to look at. We can't just immediately like that say, I know what the current is. Like in the previous circuits that we had, I don't have anyone right here, where we just had a single battery and a single resistor, just V over R, we get the current, we're done. But here we can't do that. And so we want some combination of rules that'll let us turn this network of 7 resistors into a single resistor that models that whole thing, so that it can do V over that single resistor with some value to be calculated to get the current I. That's the purpose, right? The how, this is just a derivation of that, okay? And if you don't understand the derivation necessarily, just remember that all it's derived from is that the fact that resistors in parallel drop the same voltage and resistors in series have the same current going through them, okay? But the conclusion of that is that if I have 3 resistors right here, R1, R2, and R3, and I want to write their total resistance, it's just R1 plus R2 plus R3. That's the easy one, right? If I have resistors in parallel like this, then I write their equivalent resistance as 1 over R1 plus 1 over R2 plus 1 over R3. I have an example to explain this. So let's go through this example first, and if there's still questions, then we'll go through it again. But let me first walk through this. This stupid. So how do we find the current flowing through the battery in this circuit? It's the same thing. We can't just do it quickly. So first, we're just gonna go from the right and work towards the battery. We're gonna work in the opposite direction, right? So suppose first we want to combine R4 and R5 into a single resistor. How do we do that? Someone tell me.
Add them together.
Add them together. Yeah. Okay, so we do that. They're in series. So we add the resistances. 8 plus 2 equals 10. So we just replace those two resistors with a single resistor. We're going to call it R45, which has a resistance of 10 ohms. Okay? Now let's look at the next thing. We have R3 in parallel with R45. Okay? So how are we going to combine these resistors? Avatar Nandan?
Do 1/10 plus 1/10, which is 2/10, and then do 1/2, which is
Yes,
5.
exactly. That's exactly right. 1/1/10 plus 1/10 is 1/2/10, which is 10/2, which is 5. Does that clarify the formula? I know the formula for parallel resistors looks really weird. Even like now, it's such a weird looking formula, but it makes sense. But this is how you use it. It just looks weird. Are we clear on how to use that formula? Is anyone unclear on how to use that formula? Isn't there a trick? Yes. And that trick is, yes. But that trick is just this. It's just a restatement of this. It's using the same formula. It's just mathematically convenient. We happen to see that. But also it makes sense, right? You think about parallel resistors like angry siblings fighting over some candy that their parents gave them, okay? And one sibling is a lot more angry than the other, right? And so the really angry sibling has not much resistance. They're gonna steal all the candy, the current, and the other resistor has a lot of resistance and is not gonna steal much candy, okay? But there's only a set amount of candy. If those two siblings are trying to steal the same amount of candy, I don't know, this is a stupid analogy. The point is, if they resist the same amount, current will not prefer to go into either one, right? They resist the same amount, right? But if this R45 was way more resistive than R3, then a lot less current's going to go through the right side and a lot more current's going to go through R3. Do we get that? I don't know why I was talking about candy. I just want candy. Okay, so we have a 5. So we replace the 10 and 10 with a 5 ohm resistor. Now we're going to combine these three series resistors, R1, R2, and R3. So just say it out loud. Tell me what it is.
20
20.
ohms.
Yeah,
Yep,
20
got it.
ohms.
Add them together, we get 20, and now we have that. And look, we're done. All we have is a battery and a resistor, and this is easy. What's the current flowing through the battery here? Not 0.4 amps. Not 100 amps either. 4 amps, yes. Remember, not 4 amps. What am I saying? Sorry, it's not 4. Careful. 1/4. Yes. Sorry, you guys were saying it so much. You mixed me up as well. Remember, V equals IR. Okay. The amount of resistance that this has drops that voltage. So this 5 volts dropped across the 20 ohm resistor. 5 volts over 20 ohms is 0.25 amps. Can I show the equation again for parallel resistors? Yes. So if you haven't written it down, at the very least, write down the equation. And since this is recorded, it'll be on Zoom for you to rewatch the derivation and go through the slides if you were confused about that. But at the very least, do write down the equation here. Okay. And you can also Google it whenever you need to, and that's cool. I'll give you like 20 more seconds to write it down. You guys, that's 0.25. Yes, that is correct. Okay, so that was that example. Okay, so for now, I'm gonna move on from those resistance things. There's gonna be a ton of practice that you're gonna do with this, right? That we're gonna put on the problem set. Because it is an important thing, but the problem is simplifying series and parallel resistors does not get you very far. It's an important tool, but as far as actual circuit analysis goes, it's just like the first step. And really, there's a much more powerful technique that we need to know. And this is the technique that even now, like in actual designing of circuits, this is what I use when I'm trying to do circuits on paper. It's the most important, the quickest, the simplest technique for analyzing circuits. So this is a big trick that you guys should know. So here I want you to tell me how much power is dissipated by the resistor R2. Just right off the bat, we have two batteries connected to this circuit. And we have this weird T shape that's not series R parallel. It's actually called a Y, and we'll talk about delta Y maybe later. But it's a weird shape, and so this is not at all clear how to simplify this. Would this be a short circuit? It wouldn't be a short circuit. So I think maybe you're looking at this bottom wire and thinking that's a short circuit. But because we have resistors and there's no loop that you can draw that has only wire, it's not a short circuit. Any loop that you draw has some resistance, so we're okay. But yeah, that's a good thing. For anyone who doesn't know, a short circuit is if I were to have a battery and a wire with no resistor. What that does is it causes a battery and a wire with no resistor basically means I'm sending like hundreds of amps through that wire, and I will just light a fire, basically. Now, most circuits don't let you do that, but you're gonna do damage in general if you don't have resistance. Infinite amps with the perfect wire, exactly. So, I don't. It's not 250 watts actually. Remember, this is a complicated circuit, so it's not gonna be simple to solve it. But it's good that good to try. So, what is the voltage below R2? Someone tell me. What is the voltage below the resistor R2? 0. It's ground, right? You see that arrow? That's the ground arrow. That tells us where 0 volts is defined to be. Okay? So if we can find the voltage above R2, then we know the voltage dropped by R2, then we can easily find the current, right? So that's our task. We need to find the voltage at that point. We call it a node, at the node above R2. Okay? Well, what is that voltage? Can someone tell me? What is the voltage above R2? I see some guesses. Not only are the guesses not right, but it's not easy. It's not immediately obvious. So the voltage above R2 is a bunch of question marks right now. We don't know what it is. We have to. I realize I fooled you guys. You guys are trying to guess. I should have maybe clarified that it was not. Okay, don't spam, please. Hey, Kavir, please stop. Let's call the voltage above R2 Vx. Okay, we're just gonna call it a variable. And now our task is to do some algebra and solve for Vx. We do look at it in terms of currents. That's a good thought. So, first, this is kind of an assumption. So this technique is called nodal analysis. And when we do nodal analysis, to make sure we don't mess up signs, we assume Vx is very, very high. Okay, we assume it's a high value, such that all current flows away from it. So here's the first example. If I wanted to write the voltage going or the current going through R1, first we write the voltage dropped by R1, which is equal to Vx minus 10 volts. Do you guys see how we got that? So if maybe it's even more clear. Let me annotate. So the voltage right here is 0 volts, right? We all agreed on that. Okay? Then as we go up, as we trace this circuit through the battery, when we go through the battery, we gain 10 volts. Okay? So now, once we reach this point right here, we're at 10 volts. Okay? So actually, we know the voltage of this point, and we've assigned a variable Vx to the voltage right here. Okay? And so the voltage dropped across this resistor in that direction is Vx minus 10. Why do we assume Vx is very high? Because it makes us not mess up the signs of the arrows. You don't have to, and you can still do it right, but you have to be careful about the signs if you don't do that. If we just assume it's very high and that current is all flowing away from it, then we don't have to worry about doing wrong things in our algebra. What about the place between the ground and battery that is also 0? Yeah, this is also 0 volts. That's true. But we don't really care about that point, right? All we care about is what happens when we go through components. Any place connected by only wire is always at the same voltage. Okay? So this is 10 volts. This is Vx. And so the voltage drops through the resistor is Vx minus 10. Does that make sense? Why it's Vx minus 10? Vx isn't 20 volts either. I mean, it makes sense to Toby, but it needs to make sense to the students as well. Why minus 10? Because the voltage right here is 10 volts, right? So the voltage right here is Vx, and the voltage right here is 10 volts. So as we move across the resistor, we lose some voltage That's equal to Vx minus 10. But doesn't voltage also go the other way on R1? Yeah, and so if I wrote it going the other way, it would be 10 minus Vx, right? 10 minus Vx if we were going in this direction, right? We're saying 10 is the high voltage and we're saying Vx is the high voltage and 10 is the low voltage, right? And that's why we drew this arrow. That's why we're assuming the current goes in one direction. Yeah, so I guess you can say, let's go to even like a previous slide that will show this. So there was this example right here. So in this example, you see they gave like explicit positive and negative arrows. So it's like positive and negative, right? So you lose 4 volts in that direction. Or equivalently, in this direction, we lose negative 4 volts, okay? It's this, if you go in the opposite way, you change the sign, right? Which makes sense, right? From here to here, from the bottom to top across the battery, I gain 6 volts. From the top to bottom of the battery, I lose 6 volts. Okay, it's the same thing. Does that make sense? Okay, I'm gonna assume we're good on what it means to go to lose and gain voltage. So let me go back to our example here. So Vx minus 10, because remember this point right here, I can't draw. This point right here we identified is at 10 volts. Okay. 10. Oh my God, the stupid Zoom chat. Okay. 10 volts. And so Vx minus 10 is the current dropped by R1. Voltage over resistance equals current. So Vx minus 10 divided by the resistance, which is 5, gives us the current in that direction. Okay? Does that make sense? What we did there? Are the steps clear? Okay. Now I want someone to just unmute and tell me what's the current going through R2? Yeah, I'll let someone go ahead and guess, and then yeah, Neil, go ahead, and then I'll explain it again.
Well, maybe it's like 2 amp.
Well, we don't know the value of Vx, so it's going to be some algebraic expression, right? I think I'll explain it for this one. So first of all, we need to identify the voltage before and after the resistor. So the voltage after the resistor is what? Someone tell me what the voltage right there is. Or just say in chat, whatever. 0. Yeah, should be second nature, right? We see the ground arrow, we know it's 0 volts. The voltage right here is what?
Vx.
Vx, exactly. And so what is the voltage dropped across the resistor in the direction of our current?
Vx.
Vx minus 0, which is just Vx. And so what is the current through that resistor? If it drops Vx and it has a resistance of 10 ohms, what is the current?
Vx divided by 10.
Yes, exactly. Don't be afraid to just unmute and spit out the answer, right? If you get it wrong, that's good, right? Mistakes are good. Earlier, a few days ago, at like a lab meeting in front of this professor who has like, he's really important, I like completely blurted out the wrong answer and I felt terrible. But then after the meeting, the professor came up to me and he's like, thank you for speaking, because he was so sad that no one in his meeting was talking. Okay? Genuinely, you gotta like just speak up, and it makes me happy when people get things wrong. You just gotta speak up, okay, all the time. So, but yeah, and so those are the steps we do right here. Vx minus 0, and then IR2 is Vx over 10. Now let's do the same thing for R3. Someone just unmute and try to explain the process for me. Actually, first, I'll look at the steps. So what is the voltage dropped by R3 in the direction of the current? It's a tough question, but someone give it a go.
Vx minus 20?
Yes, Vx minus 20. You got it. Because remember, we're at 0 volts right here. Okay, 0 volts. We go through the battery, we gain 20 volts. So we're at 20 volts right here. And that means we're at Vx before the resistor, we're at 20 after the resistor. So the resistor drops Vx minus 20. Okay? And the current, what is the current to that resistor then? Anyone?
Vx minus 20 divided by 5.
Yes, exactly right. That's what we do. So now we have, oops, excuse, oh no, I revealed the answer. That makes me so sad. I didn't mean to do that. Okay. So doesn't electricity flow from negative to positive? So I think what you're trying to tell me is that like electrons flow away from negative charges and towards positive charges, and that is true. That is right. But remember that assumption that we make when doing circuit analysis of it's called conventional current, right? Where we talk about the flow of positive charges. It is kind of just for convenience, and we're lucky, not lucky, the math makes us lucky that it works out the same. But you're right that in reality, it's electrons flowing, and they're actually flowing in the opposite direction that we're drawing it. But we're going to talk about positive charges. Can I explain R2 again? Yes. So the voltage below the resistor R2 is 0 volts, right? That's just because ground is right here, okay? The voltage above R2 is Vx, okay? And so as we go in the direction of current, we go from Vx to 0 volts. That means Vx minus 0 is the amount of voltage dropped by R2. And so the current is that voltage drop divided by its resistance, which is Vx over 10, which is what I wrote right here. Is that any clearer? Okay. And again, this is not easy. Like, I mean, I have college student friends who struggle with these things the first time they see it. So if you're confused, don't worry. You should go over the lecture video again. You should do the practice problems, and I promise you it will be solidified. So don't be disheartened if you're not getting it at first. Okay. So now what we want to do is write out Kirchhoff's current law for this junction right here. But there's only current going out of the junction. What I've said Kirchhoff's current law was what goes in must come out. How does that make sense? How can we, there's nothing going in, so how is there stuff only coming out? What's the answer? How can I only have currents going out? Yes, Satvika?
It might be wrong, but what I'm thinking is it was in the whole time.
That's not quite right. That's an okay guess. But remember, the rule that current can flow in, like what goes in must come out, it's still true. The secret that I briefly flashed on the screen is that these currents, these IR1, IR2, IR3, can be negative. There is nothing in our math, nothing in our circuits that has made it so that these currents can't be negative. And if they're negative, all that means is it's flowing in the opposite direction of this arrow that we drew. So for example, this arrow right here represents I1, okay, or IR1. If we do some math and find out that I1 is actually negative, all that means is that I1 actually flows in this direction, okay? And that's completely fine, right? That's okay. We separate the math from the physics here, right? The math doesn't care if it's positive or negative. Numbers are numbers, okay? So are we all adequately fine with the fact that these currents can be negative and that life goes on and that nothing is ruined? We can be on our merry way. Okay. He's not an instructor for this class. He's an instructor for a different class. So it has negative charge. It's not like that either. It's just if it were going in this direction, that means this potential is higher than this potential right here. If it's going in this direction, that means this potential on the left side is higher than the potential on the right side. I realize I'm saying the word this a lot, which is making it unclear. But all that the current direction means is which direction has a higher potential, right? It's what we talked about in lecture 1. Current flows from high potential to low potential. We assumed Vx was high potential just so that we can draw the arrows and keep our signs consistent. But Vx could be low potential and current could flow there, and that's completely fine. Okay? So let's go ahead and proceed with our analysis. Since there's no current flowing in, but there's all current flowing out, that means that the total sum of all the current flowing out is 0. Does that make sense? I know that's a really weird thing to say. So there's no current flowing in, so there's no current flowing out. So the sum of all the current that flows out is on the left. The sum of all the current that flows in is on the right. It's just, since there's no current flowing in, that sum of the current flowing in is 0. Does that make sense? Does this equation surprise anyone?
So it's like saying 0 plus 0 plus 0 is 0, right? In a way, because all the currents are equal to 0? Or no?
Not quite, not quite. So
Okay.
it's equal to 0, but it's not all the currents are not necessarily 0. Like IR1 and IR2 could be positive, but then IR3 could be negative and cancel them out.
Okay.
Right? And that's actually what we'll see. Not that specific combination, but some of these currents are positive, but the other one is negative, and so it'll add up to 0.
But
Yeah,
it just cancels it others out.
Yeah.
Okay.
So let me explain it one more time. Okay. And then I'll use a different color. Maybe this is more is the orange more visible? I think it's more visible. So when we were writing out these voltage drops, assumed that the voltage is high here, high. I'll write high if I can draw with my cursor. High. And we said it's low here. Low here. Said it's low here. And we said it's low here. Okay? And so since we said it's high here and low here, we're just going to assume that the current goes in this direction while we do our math, from high to low. Okay? So this current right here, that's IR1. IR1. Because that's the current flowing through resistor R1. We say the current flows from high to low, and since the voltage, that resistor drops Vx minus 10, that current is Vx minus 10 divided by 5, and it flows in this direction. However, what if the voltage here was actually higher than the voltage here? And what if the current in reality, in the actual circuit, was flowing from the left to right? Also, Satvika, that is correct. Good job. What if the current was actually flowing from the left to right? That's completely fine. All we're going to see is in our final equation, IR1 is negative. That's all that happens. And indeed, we will see IR1 is negative when we solve the circuit. Okay? That's all it is. Negative signs are completely fine. It just means if the current's going in the opposite direction than the one that we drew originally. Does that make sense? Are we a little more clear on that? Is IR2 positive and IR1, IR3 negative? IR2 is positive, but we'll actually see that, sorry, IR1 is positive, IR3 is negative. That was my bad, I misspoke. IR1 and IR2 are positive, IR3 is negative, but that's not clear right now. We'll solve for that, and then we'll find out that this is the case. So, let me clear these drawings. Okay, sorry. Okay, so first, we substitute in the expressions that we have for IR1, IR2, and IR3 in terms of Vx. We write it like that, okay? So this first term is that, this term is that, and this term is that, okay? That's all we did. We just substituted in what we had previously solved for with Ohm's law. Then we multiply both sides of the equation by 10, okay? So 10 times this term on the left gives us 2 times Vx minus 10. 10 times Vx over 10 is just 10. And 10 times this term gives us 2 times Vx minus 20. Okay? If that's not clear, then I want you to write that out on paper and do the math yourself. Okay? I encourage you to do that, actually. Then we just do a little bit of algebra, which you should do yourself. I'm not going to do that here. You should do the algebra yourself. But in fact, please do the algebra yourself. We find that we get 5Vx equals 60, or Vx equals 12 volts. And so just like that, we solved for the voltage right here, the voltage Vx. Now we know that voltage is 12 volts. Okay? So once we got these currents and wrote down this expression, once we did these two steps, it was all just math. There was no more thinking about circuits and potential and resistors anymore. It was just, let's go through the numbers and figure out what Vx is. Okay? And since we've done that, we know that voltage right there is 12 volts. So someone can tell me pretty quickly, what is the current through the resistor R2? Yeah, 6/5. Oh, sorry, something. But yeah, it's 6/5, 1.2 amps. And so how much power does it dissipate? It's like a number. It's like I think 101.44 watts, I think is what you have. But the point is, at that point, you can just use the formula and you're good. So are we clear on the steps that we follow? Let me run through it one more time. It's okay if we don't get to all of mesh analysis today. I'm fine with that. Mesh analysis, because this is really in every class that we'll do from today onward, we're going to be using nodal analysis, right? Like this is the most important circuit analysis technique. In fact, this is what circuit simulation programs use to simulate circuits. This is like the method that they do behind the scenes with some code, okay? They take a net list and anyways, it's the spice structure, it doesn't matter. So what were the steps that we did? I'll just run through the steps one more time. First, we need to figure out what the current through R2 is. And so to do that, we look at the voltage above and below R2. But the problem is, we don't know what the voltage above R2 is right now. So we assign a variable to that voltage, and now we're going to go through and do some thinking and figure out how we can write an expression to solve for that voltage. So to make our lives easier, let's assume Vx is a very high voltage and that all currents flow out of that node, okay? So we're going to say Vx is higher than this and current goes in that direction. Vx is higher than that and current goes in that direction, and Vx is higher than this and current goes in this direction. That may not actually be true. And if it isn't true, then we'll just get negative numbers and that's fine. It's all good, okay? So the voltage through resistor R1, the voltage right here is 0 volts because that's ground. And so we gain 10 volts through the battery. We gain 10 volts. I shouldn't draw an arrow. So right here, 10 volts. And so the voltage drop in the direction of the current. Always remember, we look at the voltage drop in the direction of the current is Vx minus 10 volts. And so the current is that voltage, Vx minus 10, divided by 5. Now we do the same thing for R2. The voltage above it is Vx. The voltage below it is 0 volts. So it drops Vx minus 0, which is equal to Vx. And so the current is Vx over 10. Do the same thing for R3. It's 20 volts to the right of R3, Vx to the left of R3. We're saying current is going towards the right, so Vx, which is on the left, minus 20, which is on the right. That's the voltage dropped by R3, Vx minus 20. And the current is that voltage divided by its resistance, which is 5. So Vx minus 20 divided by 5. Now, we need to write out KCL. There's no current going in. That's this 0 on the right side of the equation. But when we write KCL, the Kirchoff's current law, what we're writing is the current going in equals the current going out, right? But here there's no current going in, or there's no current going in. So that's the right side of the expression. That's just 0. And all these currents on the left side are going out. It doesn't mean that they're all 0, because some of them can be negative, okay? And now from here, it's just math, which again, please do the math on your own and see that the equations work out. I don't get it. So if it's still unclear, there's 2 things to do. Number 1, rewatch the lecture video, because it's not obvious. It is a difficult concept to get, and go through the explanation again. And if that still doesn't make sense, please email me. I can answer your individual questions. And if it's like, if you really, really want help, I'm happy to give you like a one-on-one, like tutoring kind of thing. I'm happy to help like that as well. But just keep in mind, this is not easy. So it's okay if you don't get it. It takes time. And we're going to do a ton of practice with this over the next few lectures. So it'll really get solidified. Okay. So there's only 10 minutes left. So we have some time. I'm gonna go through mesh analysis. And yeah, go to office hours today at 9 p.m. and we'll all be there. So Rena can help you, I can help you. The other guy who hasn't shown up yet, but he'll be here next week, will help you. And that'll be good too. Yeah, at 9 p.m. today, same Zoom link, 9 p.m. Eastern. So the other method that we have available to us in circuit analysis is mesh analysis. Okay. Now, the thing is, I am not a big fan of mesh analysis. Personally, I do not use this method as much as I do nodal analysis because nodal analysis will work wherever this method works. Jay Sani, you'll see him next week. He's just been busy this week. He hasn't been able to make it, but he's been helping with some of the problem sets and stuff. But yeah. So nodal analysis is all about assigning variables to voltages and solving for voltages at the various nodes in the circuit. Mesh analysis is all about assigning variables to currents and solving through currents in the loops in a circuit. Okay? Now, as it turns out, as long as every component in the circuit touches at least one mesh, as long as we draw a loop that touches all the components, we get the exact same results. Okay? So we could draw these two loops, loops 1 and loop 2, which would probably be the obvious choice, right? Because we see these two squares. Oh, there's two loops. But we can also draw a loop around the entire outside of the circuit, and that's fine too. The reason we do that, we aren't split up as a class. And again, like I said, this is not easy. And what we've talked about today, we're going to keep using over and over again, so it'll get solidified over time. But these are also kinds of things that you need to be doing problems on your own. Me just talking is never going to be enough. You do need to do the problems to understand these concepts fully. So please do the problems that we'll send out. There's no split. It's just, this is Circuit Lab. Yeah. So, like I was saying, and the actual reason why this is true gets into a little bit deeper physics that I'm not going to speak on, but we are able to do that. But before we get started, in terms of this current going through this loop I1 and the current going around this loop I2, what is the current through R3? It's not an easy question, but someone give it a guess. I1 minus I2, indeed. Yes. And that's the current going in this direction, okay? What if I asked you for the current going in this direction? I2 minus I1. Now, the reason that is because it's because of this principle in physics that we call superposition. All that's saying is that if I have two different currents going through a thing, they just add together and the behavior is the same. For example, if I write V equals R I times R, but I is equal to little I1 plus little I2, then that expression looks like I'll write I1 plus I2 times R. Okay? And that's just equal to I1R plus I2R. So if I have two currents that are both flowing through a resistor, the voltage drops just add up. Here I have two currents flowing through a resistor. So the behavior that these currents cause, the voltage that they cause this resistor to drop, is just going to add up. That's all it is, right? Because of Ohm's law, the fact that this linear thing happens right here. I1 plus I2R equals I1R plus I2R. Okay? So it's I1 minus I2 if we're talking about the current in this direction. It's I2 minus I1 if we're talking about the current in this direction. But obviously, if they're saying the same thing, it's just one is negative because it's in the other direction. So rather than explaining the rest of mesh analysis, what I'm gonna do now is, how much time do we have? It is 2:56. Okay. Are there any questions about nodal analysis still? Let's just forget about mesh analysis for now. I give a little bit of a sneak peek of what we'll do next time. But are there any questions about nodal analysis? Because this is really the important technique. Okay. So now for the course challenge, this is the challenge, and it is certainly a challenge. Okay.